Hey, grade 8, welcome to your first lesson on mechanical systems. We're going to dive right into learning about some simple machines. Mainly today, it's all about levers and inclined planes. So concepts covered in topic 1, we're going to talk about levers, learn about the 3 different types. We're going to learn about what work is and how to calculate work, which we're going to be using a lot in this unit. We're going to get into inclined planes, and then finally, how to calculate mechanical advantage and what mechanical advantage is. So let's begin by talking about levers. And kind of already spoiled it, but what do tweezers, scissors, and a crowbar all have in common? They're different types of levers. So let's take a look at some levers and the different types and learn about them. But first, we're going to learn about work in a very general sense because we're going to be talking about work a lot as we learn about levers. Well, what is work? Work is when you exert a force on an object and the object moves. So whenever you exert a force and the object moves some kind of distance, then work was done. In all reality, it's a little bit more complicated than that, but that's the definition we're going with in grade 8. And we're going to refine this again in grade 10 when you're in Science 10. What work is, though, is it is the transfer of energy from one object or one form to another. I know that's not on the page, but that's what it's defined as. So whenever you're transferring some energy, you're doing work. And we calculate work by multiplying force and distance together. So force being the force exerted on the object, and then distance being how far the object moved during that time. You can think of work as energy doing stuff. It's energy in action. All right. So let's talk about levers, which is the first simple machine that we're going to study. And it changes the amount of force needed to move an object when we use a lever. It could change it to be higher so that more force is needed with the lever than would otherwise be needed, or it could make it less. If I'm using more force than what would normally be needed, well, then it's a speed lever. I'm increasing the speed of the object. If it's less force, then that's giving me a force advantage. So different designs of levers will accomplish different things. But essentially what a lever is it's a bar that rotates or pivots around a fixed point that we call the fulcrum. So the fulcrum is the fixed point on which a lever pivots. The effort is the area in which you supply the force to make the lever move. And the load is the weight that you are trying to move. So that is the thing that you are moving with the lever. So we have the 3 parts: the fulcrum, which is the pivot point, the effort, which is the force you apply, and the load, which is the thing you're trying to move. So let's talk about first-class levers to begin with. First-class levers are like your typical seesaw lever, where you have the fulcrum right in the middle between the effort and the load. So fulcrum lies between the effort or the force and the load. These types of levers can either provide a force advantage so that you can put in less effort, less force to lift the object, or it can give a speed advantage. It all depends on the position of the fulcrum. It could do either or. So for example, if I moved this fulcrum over towards the load, less force would be needed in order to lift the load. So then that would give me a force advantage. If I moved this instead, the fulcrum closer to the effort, well, then it's giving me a speed advantage. I would have to apply more force, more effort to make the load move, but the load would move faster. Second-class levers are where I have the fulcrum at the end, and then the load is in the middle. This gives me a force advantage, so it takes less effort to lift up the load. So again, load is in the middle and force is on the outside. I like to think of the first, the second, the third as having to do with the position of the load. So the first class lever, the load was at the end, right, with fulcrum in the middle. Second class lever, load is in the middle. And then the third class lever has the load at the end on the opposite side of the fulcrum. So you have 1, 2, third class lever. So for a third class lever, it's a type of lever in which the effort is exerted between the load and the fulcrum. This is giving you a speed advantage. It's making the load move faster by applying a greater force. What's interesting is discussing this a little bit with work. We know that work is equal to force times distance. You might notice here that the load is going a further distance. Okay, so it's going a greater distance than where the force is being applied. The work will be the same between what is applied here by the person, the input work, and the output work on the load as it gets lifted up. The work will be the same, but here the distance is greater, and here the distance is less. So that means more force needs to be applied here than we get out here. So higher force. Okay, and that gives you a speed multiplier or advantage. That was probably just confusing. We'll talk more about that later. So first class lever, where I have the fulcrum in the middle, it can be either a force or a speed multiplier. It really depends on the fulcrum position. Okay, so it depends on which side is larger. If I have a larger side towards the load, then it's going to be, if the load arm is longer, then it's going to be a speed multiplier. But if the load arm is shorter than the effort arm, then it's going to instead be a force multiplier. So it just depends. It depends on the fulcrum position. Second class is always a force multiplier, so it makes it easier to do the work. You don't have to apply as much force as you would if you were lifting up the load directly. And then third class levers are a speed multiplier. So you're applying more force, but the load moves faster as a result. Here again, we have all three levers on one diagram. Nothing really to say here because we've already talked about them. But again, first class, right? So load is on the ends. Second class, fulcrum load, that's 2. Third class, fulcrum force load, it's 3. I justify that the load is first here because the fulcrum is not on an end, so it can't be first. So therefore, it's first class. Second class, I still started the fulcrum, so 1, 2. Load is at 2. Third class, I still started the fulcrum, 1, 2, 3. So that's a third class lever. So that's how I think about it. You can think about it however you'd like. We have levers inside of our body. When we take a look at different muscle and skeletal systems, they're all just a bunch of levers. So for example, if I take a look at your bicep in your arm, this very much is actually a speed or a third class lever because I have fulcrum, effort, and then I have my load here. So it's a third class lever, which gives us a speed advantage when it comes to our bicep and how we can move it. If we take a look at this right here, we have fulcrum, load, and effort. So this would be like a second class lever, and then we have a first class lever when it comes to our neck and moving our head up and down. So interesting stuff. We have all sorts of levers inside of our body that are able to accomplish as a result different things. So take a look at this wheelbarrow and you tell me, do you think this is a first, a second, or a third class lever, a wheelbarrow? So our fulcrum would be the wheel here. My load is the middle and the effort is right here. So based on the fact that I have the load in the middle, fulcrum is 1, 2, 3. This is a class 2. It's a class 2 lever or a second class lever. Okay, great. And load will go up as well. What about this person pitching? Woo, they're throwing a fastball here. What kind of lever do we have? Well, this is the load, is the baseball itself. The fulcrum is going to be the shoulder thing going on. And then our effort is somewhat in the middle that the muscle's using. So this is very much going to be a third class lever or a speed advantage lever, right? Based on the fact that as a result, the baseball's going to end up going a lot faster. So I have fulcrum, effort, load. And remember again, that load is at the end. Okay, so 1, 2, 3, it's a third class lever. Last example here. I have a teeter-totter. What does that fit into? First, second, or third class? And the answer is it's first class because I have, and let's talk about it as this person right here is the load. This is the fulcrum in the middle. And then this person is the effort as they push back down, I guess. I don't know, confusing, but you get the idea. Essentially, the load is at the end, so first class, right? First class because of where the load is. All right, moving forward, let's talk about inclined planes. Inclined planes are just ramps, and what an inclined plane does is it reduces the amount of force needed to lift something up simply because of the fact that it travels over a greater distance. So if I were to lift up this box, I'd have to go from here to here. Well, if I have this box go up the ramp, it's going all the way along this distance. So I'm spreading out the work over a longer distance instead. Same amount of work is done in either case, but that happens over a greater distance, so it needs less force. As we learned already, and we're going to get more into this, work is equal to force times distance. So if the work is the same either way, if I have a greater distance, then to get the same number for work, I can have a less force. So that's what's happening here. I just have a greater distance, so as a result, less force is required. So that's how an inclined plane works. It just spreads the work over a longer distance so that less force is required. And there's only one type of inclined plane, one kind of ramp. So what is work? Let's get more into work and try to do some calculations around this. Work is when you exert force on an object and the object itself moves. It is a transfer of energy from one object or one form to another. So whenever you exert force on an object and it moves, it travels a distance, work was done. And the formula for work is really simple. It's just force multiplied by distance, or how we show this in shorthand is W, which stands for work, is equal to F times D. What you're going to see in the work that we do together is that it's going to be a dot, F dot D. That dot is the same as multiply. You will see that as time goes on, we move further and further away from using an X in math to mean multiply. And the reason why we move away from that is when we do algebra, X is often meaning unknown. So it gets confusing when we use X both as an unknown and a symbol for multiplication. So instead, we either use the dot or we don't put anything at all there, and we just say, erase that, work is equal to FD, and we just know that those two things are multiplied when they're together side by side like that. So, some information about work. Sorry, wrong slides here, I'm all over the map. So work is calculated in joules. So it's calculated or measured in joules, which we show with the unit of J. So don't confuse the variable with the unit. We represent work as a variable, as W. That's what it is in the formula. But then when we have the number, we write the unit after that number. And the unit we write after that number is joules. So it tells us what unit it's in. The same thing as feet and meters. 6 feet is very different from 6 meters. So when I'm talking about a distance, I can't just say 6. I got to say what the unit is. Force is measured in newtons, so that's the unit for force. Again, the variable is F, but the unit is N. So whenever I have a force, I'm going to write N after it. And then distance, we always represent in meters in physics, in science. So we're going to use meters for that. Again, the symbol, the variable for distance is D, but the unit is going to be M for meters. So my formula is work in joules is equal to force times distance, where force is in newtons and distance is in meters. You're going to see examples for this, so don't panic here. In fact, we're going to do one together. I want to show you the problem-solving process I'd like you to use for these kinds of questions. This is a problem-solving process that's going to serve you very well as time goes on. Okay, so it's going to seem like a pain right now of, oh, I got to write so much out, but it makes it easier if we always follow the same basic process. So you lift a box with 15 newtons of force. That's my F. So I'm going to start out by writing everything that I know. So my force, my F, is equal to 15, and the unit is N, which is newtons. So I'm going to write that. I never write a number without a unit. I always need to have a unit afterwards. I have a distance of 1.5 meters. That's the D. So D is 1.5 meters. Again, I have my unit of meters on there. Then it's asking, how much work did you do? So that means I'm looking for W. That's my work. So W is my question mark. So now that I've stated my variables, I'm going to put in my formula here and work with the formula. So work is equal to force times distance. Okay. This formula you'll always have access to on a formula sheet or whatever. So this is the formula that we use to calculate work. So work then is very simply equal to force of 15 newtons multiplied by a distance of 1.5 meters. So it's just 15 multiplied by 1.5. So let's bring the calculator over here and show you what that is. The answer is 22.5, but I want to show you plugging it in. 15 multiplied by 1.5. Press enter, and I get an answer of 22.5. So that's my joules. Work is equal to 22.5 joules. That's my final answer. So that's the problem-solving process I'd like you to use, where you have, first of all, your variables listed, your unknown, you write out your formula, you plug in the numbers that you have here into the formula, and then finally you find the final answer and state it. Okay, let's get into another example. Example 2. Your backpack weighs 40 newtons and you walk 3.8 meters up a flight of stairs. How much work did you do? Give this one a quick try on a piece of paper, okay, and then tell me the correct answer. Now let's go through it together so you can check your work. So I have your backpack weighs 40 newtons. I can see that that's a force based on the unit. So even though it doesn't say force directly, I know from the newtons that it is a force, so I can use it as one. So 40N. This is a bit of a side note that weight is force of gravity. So when they talk about weight, it is talking about a force. And you walk 3.8 meters up a flight of stairs. So my distance is 3.8 meters. How much work did you do? That's my question mark. So I have work is equal to force times distance. So work is equal to 40 newtons multiplied by 3.8 meters. So work is equal to, and I can grab my calculator again, 40 multiplied by 3.8. I get an answer of 152. So 152 joules. You'll notice when I do that, I'm not putting in the unit at all, the newtons, the meters, that doesn't go into my calculator, but I just have to make sure that whenever I write a number out at all, that I have the unit. Okay, so I can't have numbers in science without units. Third example, you can try this one out as well. Put in the answer and let's see if you're right. So you apply a force of 500 newtons to a 2-meter high wall, but it does not move. How much work was done? So I have a force of 500 newtons to a 2-meter high wall. This is where you got to be careful. That's not a distance, that's the height of the wall. The fact is the wall did not move. It says here, did not move. So the distance that the wall traveled is 0 meters. And I want to find work. So work is equal to force times distance. So work is equal to 500 newtons multiplied by 0 meters. Well, anything multiplied by 0 is 0. So the answer is 0 joules. Is this a cruel question to give you? Yeah, it is. Yeah, it's tough. But I wanted you to realize that if something doesn't move, no work was done. In order for work to be done, the thing has to move when the force is applied. If it does not move, there was no work. So let's talk about input and output work, which will allow us to talk about mechanical advantage and stuff. So the work you do on the machine is called the input work, okay, because that's what happens before you're putting it in. And then the work that the machine does as a result is the output work. So when you push down on a lever with a force over a distance, that's the input work. And then the machine as a result exerts a force over a distance, which is the output work. A machine cannot do more work as output than you put in as input. Very case scenario, it can do the same, but it can never do more. So why do we use them? Well, either to give us a force or a speed advantage. So the things it can do is they can make work easier by either decreasing the amount of effort force needed, changing the direction of the effort force, or allowing us to increase the speed of the load when it comes to a speed advantage. So those are the kind of reasons why we end up using machines. Okay, so that we can either decrease the effort needed for the force, that we can change the direction of the force that you're going to see with pulleys and stuff, or to allow us to increase the speed of the load, like a speed advantage. So mechanical advantage is all about how much easier does it make it in terms of the force required. So how much, by a multiple, less force is needed than would have been needed to just actually lift up the thing. And the way that we calculate mechanical advantage is we divide the load force by the effort force. So the load force is the force that the load goes through, while the effort force is the force that the person applies. And this allows us to figure out how much of a mechanical advantage we have from this simple machine. So the smaller the effort force needed, the greater the mechanical advantage. So let's try this out. If you need an effort force of 500 newtons to lift your friend up using a teeter-totter, and your friend weighs, there's the weight again, 1500 newtons, then what is the mechanical advantage of the teeter-totter? Let's go through the full motions for this. So we have a effort force, so let's write that out as Fe. Okay, so force effort is the E. 500 newtons. It's always going to be newtons. And then I have a load force, because the friend is the load, equal to 1500 newtons. I want to know the mechanical advantage, the ME. The me. So mechanical advantage is equal to load force divided by effort force. So I have 1500 newtons divided by 500 newtons. And that means that it has a mechanical advantage of 3. This does not have a unit. Mechanical advantage is unitless because the newtons on the top and the bottom cancel out. So what does this mean? This means that it's 3 times easier to lift your friend with a teeter-totter than it would be to just lift them up. It also means that they move 3 times less than you move the seesaw or the teeter-totter. So they lift up. When you push down a meter on the teeter-totter and they lift up, they've only gone up 1/3 of a meter. Anyways, it's interesting. So that's mechanical advantage. Let's try another example. I'd like you to try this one out first, enter the answer, see how it goes, and then I'll take it up. So you exert an effort force of 736 newtons. So that's your Fe is equal to 736 newtons. The resulting load force is 81 newtons. What is the mechanical advantage? So mechanical advantage is equal to load force divided by effort force. So I have mechanical advantage is equal to 81 newtons divided by 736 newtons. And this formula, again, you're going to have on the formula sheet, so it's not something you have to stress out about in terms of how do I remember these formulas? You get the formula given to you. So 81 divided by 736 gives me 0.11. So that means I am actually exerting more force on the pedal than it does on the actual bike itself. Right? So you push the pedal and then the load force is 81 newtons. So why does this happen? Well, because this is giving me a speed advantage, right? So I'm getting a speed advantage from this bike. So as a result, I put in more force, but then it moves way more. So that below 1 mechanical advantage represents something that's giving me a speed advantage, not a force advantage. 1 would be the perfect, like the load force and the effort force are equal. So 1 means that the force I apply on the effort, the lever or whatever, is what I get out on the load. Less than 1 means a speed advantage. More than 1 means a force advantage. With levers, we actually have a neat little shortcut we can use. So with levers, we can actually just look at the arms of the lever. So an arm is from the fulcrum to either the effort or the load. If I measure from the fulcrum to the effort, that's the effort arm, that distance. And if I measure from the fulcrum to the load, that's the load arm. So I can then take a look at those two distances and divide and figure out the mechanical advantage of that specific lever. The longer the effort arm gives you a mechanical advantage, so a force advantage on that. So let's try this out. So again, mechanical advantage is equal to effort arm divided by load arm. Okay, so what mechanical advantage is a lever providing the woman as she is pulling down on this to lift this rock? So first of all, my load arm is equal to 30 centimeters. And then my effort arm is equal to 2.5 meters. I want to know the mechanical advantage. Before we can plug in, there's a problem here, and I'm wondering if you can see it. The problem is this is in centimeters and this is in meters. I need to have the same unit in order for it to cancel out. So I need to have the same unit for both of these things. Otherwise, it's not going to be a correct answer. So I'm going to change this to meters. 30 centimeters is the same as 0.30 meters. So mechanical advantage is equal to my effort arm divided by my load arm. So I have mechanical advantage. Don't know why I put the question mark there. That should not be there. Mechanical advantage is equal to my effort arm of 2.5 meters. Just plugging in the value here, right? 2.5 meters, plugging it in. So instead of effort arm, I'm putting 2.5 meters, and I'm dividing that by the load arm, 0.30 meters. Hoping you've learned this in math before, but written as a fraction, all I'm doing here to get an answer is dividing. So I'm taking the numerator and dividing it by the denominator. So I have 2.5 divided by 0.30, and I end up with an answer of 8.33. So essentially what's happening is that this is allowing an 8.33 mechanical advantage or a force advantage. So for every Newton of force that's applied to the lever, it's doing 8.33 Newtons of force on the load. I don't know how else to say that, but it's giving a very, very strong force advantage. All right, so here's what you learned this lesson, hopefully. Hopefully from this, you can identify the fulcrum, effort, force, and load of a lever. So if you take a look at it, you can label those things. You can identify examples of first, second, and third class levers. You can calculate the work done on an object when given the force and the distance. Explain the advantage of an inclined plane, that whole idea of it allows you to lift something up with less force by going over a longer distance. Hopefully you can identify the input and output work of a simple machine. Input is what you do, output is what the machine does. Hopefully you can calculate the mechanical advantage of a simple machine, and then also explain how third-class levers are speed multipliers, which is important. And the idea behind that is simply that it multiplies the distance traveled for the load. So when you move the effort portion, when you apply the force, the other part of the lever ends up actually moving way, way more. So if I have a third-class lever where here's my fulcrum, here's my effort, and then here's my load, when I move this a small distance here, it moves it a huge distance here. So it's a speed advantage. One thing that I think of right away for a third-class lever that's a speed advantage is, you guys know those dog toys where you whip it and then the ball goes, and they give you that longer arm so you can whip it even faster? I mean, that's a great example of a third-class lever because it allows you, by making the lever of your arm even longer, it allows you to throw that ball faster than you otherwise would be able to. Okay, so that's the lesson on levers and inclined planes. Have a good rest of your day.